Okay, so this is my lab report on Lab 3, the black hole lab. Okay, so the purpose of Lab 3 is to find the mass of the black hole in regards to a star in orbital motion from position data using concepts that we have learned. By applying the momentum principle and Newton's gravitational law and implementing them in computational modeling, the mass of the black hole was found. So the motion of the star was analyzed and modeled through VIDLE using a CSV file that was provided and the given information right here, such as the star's mass, time step, and the black hole position. Using the relationship of the different FNet components and the change in momentum components, the resulting mass of the black hole was found to be 5.57 times 10 to the 31st kg. As mentioned, the two main principles that apply to this lab are the momentum principle and Newton's gravitational law. The derivative form of the momentum principle is dp dt equals F net. The change in momentum is equal to the net force acting on the object times the duration of the interaction. This screen displays the derivation. The gravitational law states that there is a force of interaction between masses in the universe. As shown here, the gravitational force has a relationship that is proportional to the product of the masses times the big G constant and inversely proportional to the distance between the masses squared. By manipulating this formula, the black hole mass will be determined with this equation, and this equation will be useful in Python form, which will be seen later in the lab. This is how it looks in Python form, as shown here. Now let's take a look at the code. Here we have the star's mass, black hole position, and the time step, which was all information provided to us to create a computational model. The data from the CSV file is imported here. Now, in the first while loop, the velocity of the star is computed during its trajectory around the black hole. This is useful for the second while loop. With information for V initial and V final, the momentum can be found because momentum is equal to mass times velocity, hence delta V and delta P can be found. This is where the main physics is applied. As mentioned, F net is equal to dp dt and is shown in the code here. Then the direction of the momentum, p hat, and the magnitude of dp dt parallel was found. By multiplying both parts, I received the parallel component of the rate of change of momentum, which is the same as the F net parallel. To find the perpendicular component, I simply subtracted the dp dt parallel component from dp dt since the sum of the parallel and perpendicular components is equal to dp dt. After all this is computed, the mass of the black hole is calculated. This is what happens when I run the code. The star orbits the black hole, and these are the various components. It's important to note that the arrows are largest when closer to the black hole. The perpendicular component is larger than the parallel component because it represents the direction of motion. The blue arrow is the perpendicular component, the black arrow is the parallel component, and the yellow arrow is the net force. As mentioned, this is the equation that finds the mass of the black hole. The resulting mass is printed, which to reiterate was 5.57 times 10 to the 31st kilograms. Alright, so to summarize, this is the flow of computations that take place to arrive at the mass of the black hole. The positional data as the star orbits around the black hole allows us to find the velocity, from which momentum can be calculated. The force components are then found, leading to the goal of the lab, which was to find the mass of the black hole. Now for the lab questions. In response to the what does it mean question, dp dt equals F net is derived from the momentum principle as shown earlier, and that dp dt is something that can be calculated from the observed position data, whereas F net is the force causing the observed motion, so we can't measure it directly. And the same thing applies for F net parallel and F net perpendicular, and the respective change in momentum, perpendicular and parallel. So F net is qualitative and dp dt is quantitative. In response to the what if question, no, you cannot tell the difference because nothing has changed except the black hole. The original positions are the same, velocity, momentum are the same for the star in orbit, so this means that the net force doesn't change. The mass is probably going to be the same as the old one. And this concludes Lab 3.